All right, today we are going to tackle one of the most important and sometimes confusing concepts in vector calculus, the curl. We're going to figure out what actually makes a vector field spin and how you can get an intuition for it.
So, if you've ever taken a physics or an engineering course, you have definitely seen this symbol, right? The del operator crossed with a vector field A. And let's be honest, for a lot of us, the first move is to just cram that big, ugly formula for the test and kind of hope for the best, without ever really getting what it means.
Well, that's exactly what we're changing today. In this explainer, we're going to attach a really simple but powerful physical meaning to the curl. It's an intuition that's going to stick with you long after you've forgotten the exact details of the formula.
Okay, so let's just dive right in. When you boil it all down, the idea of curl is actually incredibly simple. It's all about rotation.
Now, the textbook definition will tell you that curl is a vector that measures the microscopic circulation of a field at a single point. So, what does that really mean? It's basically a measure of how much the field wants to swirl or spin right at that one specific spot.
To really get a handle on this, we're going to use an analogy that I promise you we'll never forget. I want you to imagine that your vector field is like the current flowing in a river. Now, imagine we drop a tiny imaginary paddle wheel right into that water.
Okay, so look at this. It's the perfect way to see it. On the left, we have a field with high curl. You can see the water current is swirling. If you put our little paddle wheel there, the different speeds and directions of the water hitting the blades, well, it's going to cause it to spin. That spin, right there, is the curl. Now look at the right. The current is totally uniform. The water just pushes the paddle wheel downstream. It moves, but it doesn't spin. The forces on all sides are perfectly balanced. That's a field with zero curl. Simple as that.
And here's the crucial part. Curl is a vector. That means it has two pieces of information, a magnitude and a direction. The magnitude, the length of the vector, tells you how fast that paddle wheel is spinning. The direction of the vector points along the axis of the spin. And you can figure that out with the good old right-hand rule. If you curl your fingers in the direction of the spin, your thumb points in the direction of the curl vector.
All right, so we've got the gut feeling for it. We can picture the paddle wheel. But how do we actually calculate this spin? Let's get into the math behind the machine.
And yep, here it is. This is probably the formula you were told to memorize. And it looks like a monster, right? A 3x3 determinant just packed with partial derivatives. But don't let it intimidate you. Every single part of this is just a systematic way of adding up all the little pushes on our paddle wheel to see if there's a net spin.
Let's just break it down. Take a look at the z component, which measures spin around z-axis. That first term, delta A by delta x, basically tells us how the upward push on the paddle wheel changes as we move sideways. The second term, delta A by delta y, tells us how the sideways push changes as we move up. The difference between those two tells us the net twisting force. If they're not equal, the paddle wheel spins. The formula is just doing this check for all three possible axes of rotation.
So calculating the curl at every single point in a big area and adding it all up, that would be incredibly tedious. Luckily for us, there's a kind of mathematical superpower that gives us a huge shortcut. It's called Stokes' theorem.
What Stokes' theorem does is give us two ways to get the exact same answer. On the left, you have the hard way. Calculate the curl everywhere and then integrate it over an entire surface. That's like adding up the spin of millions of little paddle wheels inside a big area. But then, on the right, you have the shortcut. It says you can totally ignore everything happening on the inside and just measure the circulation of the field around the outer boundary line.
And this is just so cool, you have to see why it works. Imagine our whole surface is a grid of tiny little squares. The flow around each little internal square gets perfectly canceled out by its neighbor, because where one path goes right, the one right next to it goes left. The only bits that don't get canceled out are the ones on the very, very outer edge. It's such an elegant and powerful idea.
Theory is one thing, but let's actually see it in action. We're going to take a concrete example and prove to ourselves that this theorem really holds up.
Okay, here's our proving ground. We've got a vector field A, given here in cylindrical coordinates. We want to find the total circulation over this surface S, which is outlined by the path L. We're going to do it both ways and see what happens.
First up, the shortcut. We're going to perform the line integral of our vector field A all the way around that closed path L. This means we integrate along each of the four straight segments and then add them all up. And when we do the math, we get a result of 4.941.
All right, now for the long road, the hard way. First, we have to calculate the curl of our vector field A. We use the formula for cylindrical coordinates, and we get this new vector field you see here. Then we have to integrate this curl over the entire surface S, and after all that work, we get 4.941.
And there it is, the exact same answer. That is not a coincidence, my friends. That is the power of a fundamental theorem of calculus. All of that microscopic spinning happening inside the area is perfectly and completely captured by just looking at the flow around the edge.
So what? Why do we care so much about curl? Well, this isn't just some abstract math problem. Curl is absolutely fundamental to how we describe the physical world around us.
Now, when a vector field has zero curl everywhere, we give it a special name. We call it an irrotational or conservative field. And these fields are special because there are no swirls or vortices anywhere in them. This little property means we can describe them with a much simpler scalar potential field, which makes solving problems way easier. The classic example is a static gravitational field.
But the most famous application of curl, its real celebrity appearance, is in electromagnetism. This equation you see right here, that's Ampere's law, one of the 4 cornerstone Maxwell's equations. It says that the curl of the magnetic field, H, is equal to the electric current density, J. Or, to put it simply, an electric current literally creates a rotating, curling magnetic field around it. This is the basic principle behind every single electric motor on the planet.
So, we've seen that curl is all about the spin, the rotation of a field at a single point. And that leaves us with one final question to chew on. If curl is all about rotation, what fundamental property of vector fields is described by its sibling operator, the divergence? But we'll have to save that one for another time. Thanks for joining me on this explainer.